Okay, the mean. The sum of xi, pi. Yes? Does that feel familiar? So, my first xi is 2 passengers. This is the first possible value for x. And what's the probability of 2 passengers? Plus. And I'm adding because it's a summation, yes? And what that means is on average, if he does a large number of tours, on average, those tours are going to have 3.75 people in them. The average will be 3.75. Cool? Everybody good? All right. Standard deviation. We would take find the difference between the number of passengers and the average, and then take that times its probability for that number of passengers. And as a reminder, the formula in your formula sheet says that sigma x is equal to the square root of x sub I minus the summation of x sub I minus the mean squared times the probability of x sub I. Now, that being said, you guys remember how I told you to put these in L1, these in L2, and run the one variable stats? I would not expect you to type this in, and in fact, I would think there's a lot of potential for screwing this up when you type it in. I would much prefer you put the x's in L1, the probabilities in L2, and run those one variable stats. What are we getting? 1.08. Okay, great. All right, you guys. If I asked you to interpret what this means, you would say the average distance, or that the number of passengers varies from the mean by an average of 1.0897. For right now, what I want you guys to think about is, in some respects, standard deviation measures how spread out stuff is, yeah? Are we good? And so when we think about how spread out stuff is, I want you guys to start thinking about standard deviation is a measure of uncertainty. Okay? It measures how uncertain we are that on any given day he's how many passengers he's going to get. Is everybody good? Spread and uncertainty go together. Because that's going to become really important for the second half of class today. Standard deviation measures uncertainty. Everybody good? All right. Now, turns out when Pete does these Jeep tours, okay, he charges each person $150 for a half-day tour. Okay, so let's think this through. $150. So 2 people would be $300. 3 people would be $450, etc. Yeah. So we have this new variable C, and C is going to be the money he collects. But are you guys comfortable with me saying, how did we get each of these numbers? We took the distribution of all the possible passengers and we multiplied each one by the same number, 150. So really, C is equal to 150 times X. So X as a random variable is my number of passengers. C is going to be the amount charged for those passengers. But since he's charging the same amount for each person, what I've just done is multiplied this distribution by a constant. Everybody good? All right. Now, guys, all you have to do is go back into your calculator, and for your L1, change the probabilities haven't changed. Just go ahead and change these numbers. Is everybody good? What are we getting? 450. Say that again? That 562.5 sounds better. Which I'm going to put that in money terms, yeah? And for my standard deviation, about what? Ben, you might have given me the standard deviation. 162.56, is that what you said?
Yeah. 163.45.
0.45. Great. What happened? Yeah, and you guys, if I went back up here, right, if we think about, that chart at the bottom, each of these numbers is being multiplied by 150, yeah? So, that's all that would change, is that we're multiplying by 150. But since we're doing it to everything, that 150, we could almost, pull that 150 out front, like a factor. You guys see what I'm saying here? Okay? So, and we kind of talked about this before, that if you had a set of numbers, multiplying changes both the mean and the standard deviation, yeah? Is everybody good? Okay? So really, this is just 3.75 times 150. And this is 1.0897 times 150. That's where those are coming from. How are we feeling so far, okay? $50. Okay, at 160. All right, now. Let's say it costs him $100 to run each trip by the time he pays for the gas and everything else, okay? So now we're going to create a new variable V, which is going to be his profits, right? Which is essentially going to be how much he charges. So if he charges $300, but it costs him $100, he's making $200, yeah? So all of the sudden, that table on the previous page, instead of being 300, will be 200. So I'll call this variable V, and the probability of V, 200, 350, 500, 650, 800. You guys, what's going to happen to my mean in this case? It's going to be $100 less. So that was what, 462. What about my standard deviation? When I subtracted 100, did it get more spread out or less spread out? The spread stayed the same. Before I went from 300 to 900, so the range was what, 600? My range is still 600, yeah? So when what we're doing is adding and subtracting, the mean will change, but the standard deviation will not. Is everybody good? So the standard deviation will 345. You feeling okay? All right, so when we add and subtract, the mean changes, the standard deviation stays the same. And the one thing I want to really emphasize is that this happens when what we're doing is adding or subtracting a constant. So what I subtracted was $100 from each possible value. It was always $100 that I subtracted. You guys see what I'm saying? It wasn't a variable, it was a constant. Okay? And likewise, when I multiply or divide by a constant, both the mean and standard deviation change. So multiplying and dividing changes both. Adding and subtracting only changes the mean. The standard deviation would remain the same. So let's look at an example problem. Okay. We're starting there. Okay. So, if I need to convert a temperature from Celsius to Fahrenheit, what I do is I multiply by 9/5, and then I take that answer and I add 32 to it. Is everybody with me? Okay. So the first part I'm going to do is the 9/5 C. Is everybody with me? And when I do the 9/5 C, what will happen to my mean? If I multiply by that constant of 9/5, will my mean change? By multiplying by 9/5. So what is 34 times 9/5? 306/5, which is, 305 would be 61, so 61.2, yeah? And my standard deviation would be 3.6, yeah? After I multiply by the 9/5, I'm going to add 32. Will adding 32 influence my mean? Yes. Will adding 32 influence my standard deviation? Okay. So my mean in Fahrenheit would be 94.2. Does that look right? Nah. Sure doesn't. 93.2 degrees Fahrenheit. But my standard deviation in Fahrenheit would still be 30.6 degrees Fahrenheit. So the 9/5 influenced my standard deviation, but the 32 did not.
Why would you change it from,
You good?
yeah.
Okay. According to Babies R Us, the temperature of a baby's bathwater should be between 90 and 100. So if I buy this specific, is it faucet? Okay. And I have it set to baby safe. So the mean would be 93.2 degrees Fahrenheit. Standard deviation would be 30.6 degrees Fahrenheit.
Where'd you get 93.2?
That's my new mean.
Oh.
And 90 to 100. Where do I find this in the calculator?
Normal CDF.
Normal CDF. .73.
.783.
Did we all get .783? Would you buy this faucet? I wouldn't. If it's saying that if the probability it's going to be a safe temperature for a kid is just over 3/4, like think about how frequently the temperature would be not safe. That feels icky. All right. So far, how are we feeling? All right. I can make it a little bit worse. And we all know, if I can, I probably will. Okay. Big idea.
Would you want to say 0.7825 or 78.25%?
I don't. Theoretically, I don't care. I have a slight preference for the decimal because of where we're going. The stuff that we're going to start doing in units 5 and 6 in particular, we're going to want to start thinking about proportions as decimals.
Will you have to put it in percents on the AP test?
No. And in fact, I think on the AP test, like multiple choice questions, probabilities are given to you in proportions, not percents. Okay. You guys. Everything we just talked about was adding / multiplying by a constant. Where we're shifting is adding or subtracting a variable. And I want to make sure we understand the difference, okay? So what I want you guys to think about is you guys know there's 2 pints in a quart? Is everybody with me? Okay. Now, if I had something in quarts and I wanted to figure out how many pints were in that quart, right? I would just multiply by 2 to convert the pints into quarts. So if I go down the street, go to Giant Eagle, buy a quart of chocolate milk, which I might actually do today because I'm running low and that's what I put in my coffee in the morning, okay? I go buy a quart of chocolate milk. Is it going to have exactly 1 quart? Is it going to have exactly a quart in it? No. So it might have, like, let's say it has 1.02 quarts. How would you convert that to pints? You would multiply by the constant 2. Is everybody with me? We good? Okay. Now, is that the same thing? And I would get 2.04, right? Are you with me that that is slightly different than I go down there and I buy 2 pints of chocolate milk? Now, is the first pint going to be exactly 1 pint? But could I take that amount and double it to get both pints? No, because is the second one exactly 1 pint? The 2 pints are variables. Do you guys catch the difference there? So if I were to be like, oh, I can double it, and it would make sense if I'm using like a conversion factor to multiply by 2. But if I have 2 separate ones, now I'm adding together 2 variables. Because both of them are going to be close to 1 pint, but not perfect. Is everybody good? Okay. So, when I am adding or subtracting variables, the mean will be the sum of the mean of the sum will be the sum of the means. I know that feels weird. The standard deviation of the sum will not be the sum of the standard deviations. However, it will be the sum and this is, I kind of emphasized the idea of variance last week, of the variances of the two things. Sometimes we call it like the Pythagorean theorem of statistics. And when you look at geometric models of probability, it actually does kind of work out that it is a Pythagorean theorem thing. Okay. So let's go ahead and say that the mean of a pint of milk in ounces is, 16.1 ounces. And the standard deviation is very small. It should be like maybe 0.25 ounces. Is everybody good so far? So if I go and buy 2 pints of milk, I'm basically adding together pint 1 plus pint 2. And we don't know that the 2 pints are the same, so while they both come from the same kind of population distribution, we don't know that they are the same. Is everybody with me? Okay, so what is going to be the mean of that sum? Well, it would be, on average, the first one's going to be close to 16.1, and the second one's going to be close to 16.1. So the overall mean is going to be 32.2 ounces of milk. The standard deviation of the sum will be the square root of 0.25 squared plus 0.25 squared. Give or take, yeah. You guys, what happened to my standard deviation? Did it go up, go down, stay the same? It went up, but it didn't double. Is everybody with me? Okay, now, at the very beginning of class, I wanted us to start thinking through standard deviation is a measure of uncertainty. In some respects, this is the uncertainty of 1 pint of milk. Are you surprised to see that we have more uncertainty with 2 pints than we did with 1? It makes sense that we have more uncertainty, yes? Okay. Now, so, in your heads, guys, I want you to remember this. 2 variables have more uncertainty combined than one of those variables, yes? And the uncertainty from those 2 pints of milk is already there no matter what we're doing with the values. So if I were to instead say, I'm going to take 1 pint and 1 pint, and I'm going to subtract, I'm going to find the difference between the 2. I still have the uncertainty of 1 pint and the uncertainty of the other. So whether I add those numbers or subtract those numbers, I have the same amount of uncertainty. Is everybody with me? So what I want to point out in these very fancy formulas is that when I'm adding together or subtracting the means, my means are actually positive. I either add or subtract based on what I'm doing with the means. The standard deviation is always adding, so even if I subtract 2 values, I have more uncertainty because I have 2 different distributions I'm pulling from. So let's work. I don't know if we'll get all the way through this example set, but yeah.
What's the scenario where we'd be subtracting means?
So let's say we were looking at how often is Miss Meister faster at the mini crossword than Mr. Richards. we would take his average and we would take my average and we would say, when is mine greater than his, right? Which would be, well, then we would say, I'd subtract to see if I'm greater or less than his, right? Does that make sense? So it's like, there's plenty of opportunities. And if you'll look tomorrow, I have combining random variables some more. We're going to have lots of opportunities to practice this because it's a skill that feels uncomfortable for kids. Like, I built in the time for us to have that extra time. Is everybody okay? Like, I get that this doesn't make sense right now. It's not going to make sense at first. We practice with it. It'll start making sense. I promise. Okay. Real quick. All right, so what are the mean and the standard deviation of the hours worked? So 3.3 hours for the mean. If this were a free response question on a test, guys, they would expect to see this. What was the standard deviation? 1.4? 1.1 hours, great. And again, if this were the test, they would expect to see so far, are we feeling okay? This should be starting to feel, this concept should be starting to feel a little bit quicker. Okay, so along with your job, you get a $20 allowance. So your earnings are going to equal your allowance plus how much you earn at your job, yeah? So are you guys with me that it would be $20, because that part's always $20, plus, and then you're making $15 an hour, yeah? So that would be 15 times however many hours you work. All right, so what's your mean earnings going to be? Will the $20 affect your mean earnings? Will the $15 affect your mean earnings? $15 per however many hours. So both of them change with the mean. So you're going to do 20 plus 15 times the mean hours. $69.5, or $69.50. Okay. Now a way to help you guys kind of think through. You guys, does the $20 from your parents change the uncertainty about how much money you're going to bring home? Because it's always the same amount. There's no uncertainty with the 20. Yeah. The only uncertainty is the uncertainty with the 15. So we would do. Hence, the standard deviation only changes by doing 15 times the 1.1, which is $16.50. I think this is where I will stop so that when we start on the next page, We got a little bit of review, but not too much. We'll finish out the notes over combining variables tomorrow. You'll have Friday to work the homework review and the quiz. The quiz review and the homework. Your quiz is going to be on Monday.